Well, I'll be talking about the formation of Gale Crater specifically, so the crater that MSL will be hopefully landing in successfully. But most of the talk is more about the general impact cratering, so what happens when an asteroid hits a planet. So a brief talk outline. I'll first start off with why Gale Crater is particularly special for MSL to land in and as a crater in general. I'll then be going through how we can use craters to find the age of a planetary surface. A quick touch on what is an asteroid, because of course there's so many different, there's meteors, meteoroids, planetoids, so what is an asteroid? I'll then have two different examples for you today. The first is what happens when a 50-meter asteroid hits the Earth, and the second is what happens when a 12-kilometer asteroid hits the Earth. Now that's a very specific number. The 12-kilometer is about the size of the asteroid we'd expect to create a crater the size of Gale Crater. And so I'll finish off on what did Gale Crater look like when it had first formed. Okay, so this is just an image of Gale Crater. So you can see the crater rim here, and then this large mound in its center. I've highlighted the MSL landing ellipse in yellow there. You can see from the scale bar that this is a gigantic crater. It's about 96 miles in diameter. So if we look at this in topography data, now those of you that were here for Shane's talk saw some of this topography data. So you'll be used to the yellows and the oranges being the high ground and the greens and the blues being the relatively low ground. So you can see that you've got an elevated rim surrounding the crater, which is this deeper cavity in the Martian surface with this very large central mound here. So what I've done on this screen is I've taken a topographic profile through that data. So if you see the red line here is the line of this topographic profile. So if you follow through with me, here we're outside the crater. On this point of the topographic profile, so this is in elevation, and this is distance moving along this red line. So we're currently on the crater rim, and then it sinks down. So this is where the MSL will be landing, in the deepest section of this crater. And then up to the highest elevation in the crater is the central peak. Now this is not what we'd expect for a crater of this size on Mars. We'd expect the rim to be above the central peak, at least by a little bit. But in Gale's case, the mound is a lot higher than the crater rim. So, and you can also notice that the southern crater rim of Gale Crater is higher than the northern rim. And this is due to its location on Mars. Now, Gale sits on the very boundary of the northern lowlands, which are smooth. You can tell that they're lower because they've got the blue and green color in this colored digital terrain model. So it sits at the boundary of this really low region and this older, heavily cratered, rough highland region to the south. Now, the reason I can say that the lowlands are older than the highlands is purely due to the crater density. I mean, you can see that there's lots of impact craters on the southern terrain, but not so many on the north. And this is just because if a planet starts its history with a pristine surface, it hasn't been hit by anything yet, as it travels around the sun, it will meet asteroids that are also traveling around the sun, but on crossing orbits. So every now and again, you're going to get this very large impact that is going to form one of these impact craters. And the older the surface, the more impact craters have collected. So one way of looking at this is the same way as your nice, clean car at the beginning of a road trip is the pristine surface of the planet. It hasn't been hit by anything yet. All of those bugs that you get on the way to Phoenix, it hasn't been hit by those yet. But if you go on a long enough road trip, over time you accumulate more and more bugs on your windshield. And so the longer the road trip, the more bugs on your car. So very old, unaltered surfaces on planets and moons that are inactive, like the Earth's moon here. They are absolutely covered in impact craters. So you can see the light circles here, the dark circles. Each of these represents where a very large asteroid or a comet hit the surface of the moon. Now, you're not going to leave your car like that. The moon doesn't have an option. It's not active. There's no geologic process to resurface the moon. But you do have the option of washing your car. And the same thing can happen on geologically active bodies, is the craters can be infilled by deposition. They can also be removed by erosion. And so when the surface renews, the crater counting starts again. Just like if you wash your car, the next road trip you go on, you start accumulating bugs all over again. And so this is how we know that this section of Mars has been exposed to asteroid impact longer, and that something happened to the northern plains of Mars to wash the craters off it. And this is something that Shane's going to be going on into in the next talk. So, just for reference, I've kept Gale Crater center of the screen here. So you can see that it's a lot smaller than that impact, but it is quite a large crater. Okay, so what is an asteroid? What is hitting the surface of Mars and other bodies? An asteroid is basically a very large rock orbiting the sun. Now, there are several definitions. Some people say that dust-sized particles could be classified as asteroids because they'd still be in the asteroid belt. But as far as I know, the definition is you need to have maybe tens of meters in size, so about the size of a small car, up to 1,000 kilometers, at which point this asteroid would then be classified as a dwarf planet as well. And asteroids are remnants of planet formation, so when the planets were forming, all of the rock and ice and other material in the solar system was coming together, compacting to form the round shape of a planet that we know today. And in some regions of the solar system, planet formation didn't get that far, so we get this leftover debris. So in this artist's impression, we have the orbit of Mars here with the sun over here, and then Jupiter in the foreground. Most asteroids that we know of sit in the asteroid belt between the orbit of Mars and Jupiter. They are, of course, found on planet-crossing orbits. You might have heard of near-Earth asteroids and Earth orbit-crossing asteroids. They're the ones that we have to worry about. So, onto the examples. I'm going to give you two examples. The first one will be what happens when a 50-meter asteroid hits a planet. Now, this is my small example, but if you think about it realistically, 50 meters, having a 50-meter chunk of rock hit you, it's not very small. So this is, planetarily speaking, if that's a word, this is my small example. So a little bit of audience participation here. Who knows what this is? Meteor Crater, excellent. And could I get a show of hands, please? Who has been to Meteor Crater? Oh, excellent. That's a lot better than I was expecting, but there were some hands that were not up. It's 60 miles east of Flagstaff. You have no excuse not to go and see this crater. It is what happens when a 50-meter asteroid hits the surface of the Earth. It forms what we call a simple crater, which just means that it's bowl-shaped. This example is it's nearly 1 mile wide. It's 550 feet deep. which means that if the Statue of Liberty was sitting in the bottom of the crater, then the torch would not show above the rim. This is quite a deep crater. It's one of the best preserved and definitely the most accessible crater that we've got on Earth. Most of the impact craters they're not very well preserved. We're on an active planet. Things are getting filled in. Erosion is removing some of the rims. And they're also in really inhospitable places, like the middle of Australia, in Siberia, covered in ice, up in the very cold regions of Canada. This one is several hours drive away. So I always try and encourage people, definitely go and see this. This is an amazing example of where Earth has been scarred by an asteroid impact. Okay, so I wanted to show you what happens during crater formation, because of course the video that I just showed you, it showed you the impact and then it miraculously showed you this crater. So this video will show you a bit more of what was happening in order to get to that final crater. Now, in order to understand what's happening during an impact, we've used laboratory experiments where you have this high-pressured gas gun, but those are really quite small impact craters. There's also knowledge from explosion testing, so you get craters that are tens of meters across. But if we want to go up to a planetary scale, like really have a look at the planet tearing apart impacts that can happen, we need to go to computer simulations. Okay, so this is the asteroid here. The cavity opens up and then starts to fill in slightly. You're going to see this again more slowly. So if we watch the simulation through again, you'll see on this side will be temperature, this side will be pressure. So as the asteroid hits, it fractures the target, and you can hopefully see some red up the center here. That's where it's heating the target as well. All of that energy is heating the ground. You also have this high pressure shock wave that goes into the target, setting the material behind it in motion, opening the crater cavity. And then this ejector rains out on the surrounding terrain. And then after a while, I say a while, like 100 seconds. This is actually a very quick process, given how huge this kind of, the transport of rock is. You start to get the walls collapse in a bit, and this forms a breccia lens. So this is generally what a simple crater looks like. Now, that looked very nice and calm in the simulation. So just to give you an idea of the energy released when we have an impact crater like this, this particular crater will have released 1,000 kilotons. Now, the bomb that was dropped on Hiroshima at the end of World War II, little boy, was 16 kilotons compared to the 1,000 kilotons for here. So that's obviously a lot of energy being deposited onto Earth. So I thought instead of being general about this and the next example, I thought I'd go into, so what? What does this mean for us in Tucson? So, well, the formation of Meteor Crater in Tucson wouldn't have really been a very big thing down here. We're 300 kilometers away from Flagstaff. We would hear a bang. It would be about 50 decibels. So that's about the sound of my voice. So nothing particularly impressive there. We'd also get, 60 seconds after the impact, we'd get a magnitude 5 earthquake. That's not very large as far as earthquakes go. You might not notice it. You'll definitely notice the jingling of your glasses in your kitchen cupboards, things like that, but it's not going to destroy anything down here in Tucson. One other thing we will feel is an air blast. The impact's going to disrupt the air around the crater. But this air blast is very subtle. What we're going to get down here in Tucson is a 1.5 mile an hour breeze. So it's probably going to be nice. So if we want to compare Meteor Crater to Gale, I've scaled the image of Meteor Crater up here compared to Gale Crater, with the landing ellipse again on there in black. So Meteor Crater is really quite small fry. in terms of an asteroid impact. So on to the next example, which is the creation of Gale Crater. But just as with Meteor Crater, I've brought Gale to Earth. What would happen if a 12-kilometer asteroid hit Flagstaff? What would it mean for us down here in Tucson? So here's a video of what the crater should look like. Here you've got a much larger impactor compared to your target. It's going to put a lot more energy into the target, and so that affects the shape of your crater. Okay, so you actually, in this case, you get rebound. It's energetic enough to have forced down and compressed the Earth's surface, and it responds with uplift in the center. You also get a lot more melting and a lot more ejecta. Okay, so the energy released from the formation of a 100-mile crater, that's a lot of zeros. It's 100 million times more energetic than the formation of Meteor Crater, which makes it 1,000 million times more, 1,000 million times larger than an atomic bomb blast. So what does this mean? I've located the center of impact in Flagstaff, and so several bad things are about to happen to Tucson. And so the first one of these is thermal radiation. So much energy has just been deposited that it needs to be released somehow. We're going to see a light blast. There's also going to be thermal radiation. So this means that this side of the United States is going to be getting a bit of a suntan. Now, we also have an air blast to contend with. It's going to be worst in the southwest, but the whole of the United States is going to feel this. We're also going to get all of that rock debris pushed out from the surface. It's going to land very heavily in Arizona, and then it's even going to give a fine ash coating to Canada and down into Mexico. The earthquake is going to be even more widely felt. The central dark green area, or the slightly less transparent green area, is your strongest earthquake. So obviously Arizona has been taken out, but then all of Northern America will feel this, and Central America. So here is the size of the would-be impact crater compared to the state of Arizona. So you can see the FLA of Flagstaff there. So this would literally take Flagstaff off the map. But what would we feel down here in Tucson? Well, the order of play, 10 seconds after the impact here, we would get the thermal radiation hit us. 60 seconds after impact, we're going to get a really big earthquake. If you survive that, you will then be rained on by rocks 4 minutes later. And then 15 minutes later, you get the air blast. Now, this is not going to be that lovely 1.5 miles per hour breeze that Meteor Crater would have created. So, the thermal radiation. I've colored in the fireball radius here. Now, this isn't just the thermal radiation. This is the hot, vaporized rock and burning plasma that will spread out as a fireball. If you know someone in Scottsdale, they'll be on fire at this point. What we would see from Tucson, we would see a fireball that is 122 times larger than the sun is in the sky. And at 10 seconds, we get the thermal pulse. Now, the thermal pulse, it won't necessarily set metal on fire. This is from a nuclear test blast. What's happening here is the thermal pulse is going past this school bus or just a general bus. It can't burn metal and paint, but what it can do is just burn it. In a second of this pulse going past, it goes from pristine to just burnt. And that's for metals and paints. What's going to happen to us is a bit worse, because clothing and hair will spontaneously ignite as soon as this thermal pulse reaches us. We will definitely have some third-degree burns. Wood, paper, grass will be ignited. Okay. If you survive that, given that the thermal pulse actually, I say pulse, it lasts 30 seconds. We'll be down here in 1,000-degree heat for 30 seconds. So your hair will be on fire at that point. After that, at 60 seconds after impact, we get the earthquake. Now it's going to be a magnitude 10 earthquake. We have never experienced a magnitude 10 earthquake on Earth in recorded history. The largest we've recorded is a 9.5 in Chile in 1960. I should note that it's not just a case of, oh, a magnitude 10 is 0.5 larger than a 9.5. The Richter scale of earthquake magnitude is logarithmic. So a magnitude 10 is 1,000 times larger than a magnitude 8 earthquake. And it was a magnitude 8 earthquake that ripped the city apart in San Francisco in 1906. So the effects of a magnitude 10 earthquake. General panic. If you're on fire, I think you'd be, if you're not panicking already, then the earthquake is going to give you some general panic. Buildings will collapse, underground pipes broken, which means that if we don't have enough to worry about, we've got gas leaks, more fires. We're going to get those huge cracks in the ground, and in some places, depending on what's underneath, the cracks are going to release earthquake fountains. There's going to be showers of rock and ash and mud coming out of these cracks in the ground. And the magnitude 10 earthquake is going to really obliterate the southwest here. So, moving on to the 4-minute mark. So this is when the ejector, so all of that mushed up, fractured rock that has been thrown out of the crater, it'll arrive at the 4-minute mark because it needs to fly down from Flagstaff. The surrounding area here, just slightly larger than the fireball, will get a good couple of 100 meters of dense rock coating. This is what we call the continuous ejector blanket. So again, Scottsdale is not a very nice place to be. Tucson can expect to fare slightly better, as long as you consider 4 meters worth of burial in ash and rock better. The average particle size that's going to be raining down on us is 2 inches, so that's about the size of this hailstone. Now bear in mind that's an average size. You're going to get a lot more ash particles falling on you. Every now and again you're going to get a car-sized chunk come down. But the average is calculated to be about 2 inches at Tucson distance. So if you're not on, if you weren't killed by your house collapsing on you, and you're not buried 14 meters underground, and you are somehow walking around on the streets of Tucson, probably on fire, then the next thing you need to worry about is the air blast. Again, it's not 1.5 miles per hour, it's 2,700 miles per hour. You can blow out birthday candles. This will blow you to Mexico. So you might not be on fire, but you will certainly not be in Tucson anymore either. And so as this shock wave goes past, it's moving faster than the speed of sound, so we're going to get a sonic boom as well. And this is going to be a very strong sonic boom of 130 decibels. And this is going to cover all of the state of Arizona. We'll be experiencing this. Now, the effects of 130 decibels. You start having permanent hearing damage at about 90. If you stay in a 90 decibel room long enough, you'll start getting permanent hearing damage. You start getting pain at 125, so it would definitely be a painful burst. And the thing that surprised me was, as I was putting the talk together, I was looking forward to putting some examples in of, you know, how loud a pneumatic drill is. It's about 125 to 140. KISS beat an impact blast in their 2009 tour. They actually clocked in at 137 decibels, and there were reports of plaster falling from the ceiling of the stadium. Now, they only did this on their first night, because there were obviously complaints. You don't want somebody making your stadium collapse. Okay, so the effect of the wind. This is another video from a nuclear test blast. It's a very short video because, of course, once the shock wave and the air blast reaches the camera is no more. So it's just a small clip. If the buildings haven't already collapsed, this will flatten them. Glass will shatter. Cars, trucks, people, anything that doesn't have foundations of some sorts, instead of being flattened, it will just be removed from Tucson. And along the way, it will be hitting against each other. So you'll have mangled trucks that you'll find miles away. It will also blow down any trees. Anything will just be flattened. This image is an example of the Tunguska event. It was when an asteroid exploded in the atmosphere of the Earth. It didn't actually get to contact the ground, but the air blast when this asteroid exploded was enough to flatten trees. Okay. Don't worry. Statistically, we're good for another 100 million years. These sort of impacts, they're very rare in current history. They're predicted to occur only once in 200 million years, and the last one of comparable size was the famous one, 65 million years ago, the dinosaur killer. So we should have, maybe 100 million years to go before we get another, if you believe statistics. So obviously, impact is very, very bad for life on the surface of a planet. We know this from the fact that the dinosaurs are no longer with us. We know that from the examples that I've given. We would not survive. The global implications of impact are, well, deathly to life forms. But they do happen, they have happened all throughout the solar system history, and they're a very important part of solar system history. It was impacts that actually created the planets. All of the different debris molding together to form planets was due to impacts. And once the planets themselves had formed, craters have gone on to shape the surfaces of these planets over time. Now, vice versa, and this is leading up to Shane's next talk, we do see crater modification by the surface processes. So the surface of the planet is being changed by impact cratering, but then over time, the shape of the craters on the surface start to get affected by surface processes such as erosion and deposition. And so on this, I'm comparing the computer simulation that I showed you of this large crater and the topographic profile that I showed you from along here from Gale Crater. And you can see that Gale Crater is a little bit shallower than we'd expect for a fresh, unaltered crater of this size. The central peak is also higher, and it's slightly broader as well. So the take-home point from mine is the formation of Gale Crater was only the beginning of the story of the MSL landing site, and that's something that Shane will be touching on in the next talk. Thank you. Do we have questions? Yes.
So would the angle of impact make a difference on the different heights of the rims of the tower? Do they all have the same angle?
Okay. The question is, would the angle of impact affect the rims, the rim elevation on the side of the crater? It will, to a certain extent, yes. Although the predominant reason for Gale Crater having such a higher southern rim is because it actually impacted into a target that was already sloped. And so you get the higher rim on that side. So, okay. The comment was that very large impact can perhaps alter the orbit of a planet. That is very correct. It would have actually, the example that I gave for Earth, it would have affected our orbit as well. Depending on the angle, so if the planet is rotating one way and you get an impact along the kind of rotation axis, then it will slow or speed up our day by about 3 milliseconds. Now I know a millisecond isn't enough, but something strong enough to make a day shorter is obviously quite an energetic event. And for Mars, because it's smaller, it will have had an even larger effect on the Martian day. I don't want to say up to a second, but you're looking at maybe the day lengths being affected by up to a second.
Is any serious research being done to deflect objects from striking Earth?
Yes, there is. I think the serious research that is being done might be more secretive than I'm aware of. I know there are a lot of scientists that, as their pet projects, they've been working on this. Some of the ideas are, well, blow it up, try and nuke it, like the film Armageddon, that sort of thing. You can either blow up something next to the asteroid or in the asteroid to try and throw it off course. But the preferred method is seeing these things coming decades in advance. If we can see these things coming decades in advance, then we can build what's called a gravity tractor. And this is a very, very large, very massive spaceship that we would send to the asteroid decades before it comes close to Earth. And we would essentially park next to it. And the gravitational attraction between the two, between the asteroid and this gravity tractor, would pull the asteroid slightly off course. It's not going to miss us by a lot, but if it misses us, then that's the important thing. So yeah, there is research going into it.
Along that line of thinking, if we could take it out of its orbit, we could put it into a prescribed orbit and utilize it for many applications, mining, inhabiting it somehow. I spoke to somebody at Raytheon, and he kind of poo-pooed the whole thing, but I'm glad to hear what you just had to say. Thank you.
Well, a quick comment to utilizing, like changing the course of an asteroid impact. I don't think any serious research has gone into this because it would take an awful lot to do. But the idea of terraforming Mars, for example, we need to change the surface conditions on Mars if, for example, we wanted it to become Earth-like in future. And one of the suggestions is that we direct an asteroid into the ice cap and melt all of it. Give us some more gases, more atmosphere. So, good comment. Okay. Yes.
Has there been an estimate of how far back in time the bottom of the mountain in the crater will show, will be?
Oh. I think Shane might have read that. I'll talk a little bit about it. Oh, okay. Yeah, Shane's going to go on to when the crater formed, but then more so how it changed over time, how the different layers were laid down. Sorry, I'm very ahead of time. Any more questions?
Thanks. You gave us an example of Meteor Crater, and I just wanted to mention another crater that's fairly nearby in Canyonlands National Park. It's Upheaval Dome, and I didn't know if you'd known about that. I mean, there was some controversy on whether it was a salt dome that dissolved away or an impact crater, and apparently they recently found fused silica in the bottom.
I've heard the arguments for and against it. It's definitely on my list of impact craters, mainly because it's just a very interestingly eroded impact crater. So yeah, that's on the list of impact craters. There's about there's almost 200 impact craters on Earth, most of them in very bad sets of erosion. Some of them covered up. I have a couple of pictures actually. This one's Ghos's Bluff in Australia. It's an example of about a 20-kilometer crater. So because of the erosion, you've actually got less of a rim. It's less of a bowl shape because it started to be filled in. Basumtwi is about 10 kilometers in diameter, and you can see it's covered in vegetation, and there's a lake in the middle now. So the amount of deposition and erosion that's going on because there's water in there is now, eroding the crater even more, so that eventually it might start looking like Manicougan here, although this is 72 kilometers in diameter, and all you're left with in that case is this suspicious circular river that marks the trough of the crater. And then when you get even older, you can get tectonic working of the crust so that your circular feature disappears entirely, and you get this squidged up Vredefort. This is one of the largest craters on Earth, and it's definitely very old. Oh, yes?
Does the composition of the impacting object make a difference?
It does,
How much
yes.
of an asteroid?
I stuck with asteroids today. Asteroids generally hit the Earth more slowly than a comet does. So the impact would be about 20 kilometers per second. But they're going faster, so they should make more damage. But they're also less dense because they're composed of ice and rock. Whereas the asteroids, they tend to be more dense. Now, Meteor Crater was particularly dense because it wasn't just a rocky asteroid. It was specifically a big chunk of iron from the core of a larger asteroid. So that was about 8,000 kilograms per cubic meter. So that's a very, very dense object. So you'd get a higher energy yield and a larger crater the denser the object is and the faster your object is going. Okay, thank you.